All right, AP Physics. This may be the hardest part of the first unit, looking at acceleration vectors, and this is where the most misconceptions occur. So I'll take some time to walk through this and maybe do one or two problems from your worksheet. Acceleration helps us describe motion where we have velocities that change. So if we go back to what we looked at in the last video, the ball going up and down, our velocity as it releases our hand going up, this is tossing the ball up in there and coming back down, this velocity vector is getting smaller. That's a change in velocity. It's getting less and less speed as it goes up. And then as it comes back down, it's getting greater and greater speed. There's two ways to change your velocity. You can increase or decrease the magnitude of it. And you should think of that like speeding up or slowing down. And you could do both at the same time, you could change the velocity's direction. And so that would be something like this. We're going to focus all of our energy on this first one, but I wanted to show you the second one here because we'll come back to it in chapter 4. If you have a ball that goes in a circle, maybe a ball or a car, think of looking at a track or a runner going around a track. If they run at the same velocity, so they have the same distance between all these dots on their motion diagram, there's a constant velocity the whole time. They're not changing the magnitude of their speed, the magnitude velocity vector, but they are changing the direction. So if I draw my velocity vectors on here, our first one, maybe this is our V0, is going to be the same length as V1, which is the same length as V2, but they're in different directions. V0 is headed this way, V2 is headed this way, and that change in the velocity's direction is also an acceleration, which we'll come back to later on. Right now, we just want to stay with increases and decreases in magnitude, and we're going to stay in one dimension. So we're going to keep this very simple to try to do our motion diagrams with. And we want to add vectors here. Acceleration is a vector. So here's what acceleration is. Consider an object whose velocity changes from v1 to v2. So we have a change in velocity. And right now, just think of v1 and v2 getting bigger, speeding up, or smaller, slowing down. And that happens over the time interval delta t. Our change in velocity, the delta v for that, would be final velocity minus initial. We always do final minus initial. And if you do that with vectors, remember, this is not adding numbers or subtracting numbers. This is not like 100 minus 75. We have to draw this vector because we have a little arrow above it and draw this vector tip to tail. And then we draw the resultant vector, which is what this delta v will be. Okay? If we take that delta v and we divide it by our change in time, this would be how much does our velocity change over a certain time period. That's what acceleration is. And we are calling this the average acceleration because we're splitting this over a time interval, and there could be acceleration greater or less than that in that time interval, but this is just an average over that time interval. So this is our acceleration. It's a vector and it has a direction. This is how you do that on a motion diagram, and this is kind of the key concept. Don't worry about this yet. We're going to do math with this later on, and we'll use this frequently with numbers. I just want you to think about this, the idea that these are vectors, and this is how it works on a motion diagram. And this is what you want to be thinking. How do I recognize the direction of the acceleration? So we're going to find the acceleration vector for this particle diagram. We have v initial and v final. You draw your velocity vectors, which we've been doing on our particle diagrams. And we want to know what's the change in velocity from v initial to v final. To do that, we take the final velocity vector minus the initial velocity vector. Remember, we cannot take velocity vectors, or any vectors in that case, and subtract them. This is the same as doing this. Take your v final plus the negative, which is just taking our velocity initial vector and flipping it over. And if we do that, they've already done this on this diagram for us. Draw your v final, and then add to that the negative v initial. So I take my v initial right here, and I'm going to flip that arrow over. Here it is, flipped over. And then we're going to add those vectors. So adding vectors, you draw the first vector, and then at the tip of the first vector, you start the tail of the next vector. In this case, since we're in linear motion, all of yours are going to look like this, where your arrows are going the same direction or opposite directions. There's not going to be anything off at an angle. It's all going to be on the same line here. So I draw my initial velocity in the negative direction, and then this difference between the two, I start at the tail of my first vector, and I draw it to the tip of my second vector. That is my delta v. And I'm going to put my little vector symbol here. Okay, that's my change in velocity. My velocity got larger, and it got larger in this rightward direction. Does that make sense? My initial velocity was small, and I added this much more velocity in that time interval. So I got a larger velocity vector for my final velocity. And how much larger was it? It was this length larger. So if I brought this up to my diagram up here, it would look something like this. My change in velocity is right here. And this length right here that was left over, this would be my initial velocity. So I take my initial velocity, I add to it that change in velocity, and I get my final velocity. Okay, so that's how we get our change in velocity. Make sure you get some practice with this. And in your packet, spend time working on this. It has you color code it in that section on linear acceleration. Really be specific about doing this step by step, drawing your final velocity vector first. Don't change anything with it. Flipping over your initial velocity vector and drawing it tip to tail, and then the resulting vector is the delta v. Now, how do we get acceleration from that? My change in velocity is just divided by my time, which is a scalar, so maybe divided by 2 seconds or 5 seconds, whatever that time interval is, and you get your average acceleration. And so what we do after we calculate this delta v, we just take this and we're just going to say, well, that's my acceleration vector. Even though if we divide that by time, this might grow or shrink. We don't care about that right now. We just care about what is the direction of the acceleration and approximately what is the magnitude of that acceleration. And we write our acceleration vector. This is acceleration always gets written beside the dots. So acceleration vectors have to have two velocity vectors, one on each side, so we have a change in velocity. And so each pair of dots, or in this case we have 3 dots here, we will not have an acceleration to start because there's no initial velocity on this left side. There's only our starting velocity here. And we will not have an acceleration vector at the end here. We're only going to have acceleration vectors at dots where each neighboring side has a velocity vector. Now, if we draw a motion diagram like this, let's say we have 0, we have 1, and we have 2, and I'm trying to space these as equally as I can so that we have constant velocity here. I'll draw v0, write my vector notation. This is v1. The acceleration for this is only going to be at this point 1. We don't have one at 0 or 2. And if I draw that acceleration, let's go through this process again. We want to figure out what is delta v. Delta v, that change in velocity vector, is my final velocity vector minus my initial velocity vector. Well, what is that? That's going to be v1 is my final velocity vector minus v0. And this is the step-by-step that you're going to have to walk through for some of your diagrams, especially if you're having a hard time visualizing it, to see what your acceleration is. And so if I subtract these two, what would I do? I draw my v1 first. Here's my v1. I'm going to draw that. Here's v1. And then I flip over v0. Well, these are the same length. So if I flip over v0, it's going to be right here. It's going to go all the way back to the beginning here. And the distance between these two is 0. They match up. And that means that my change in velocity is 0. And this point right here, how do I represent that? I can't draw an acceleration arrow. All we do is we say a, that vector, equals 0. And that's it for right now. So if you don't have any acceleration, if you're constant velocity, you're going to label the dots between each velocity vector as the same as a0. And if you do have an acceleration, you're going to figure out what direction that acceleration is by subtracting your vectors and then writing that acceleration vector in the right direction next to that dot. Okay, let's practice that. Particle has velocity v1 as it accelerates from 1 to 2. What is the velocity vector v2 as it moves away from point 2 on its way to point 3? So we're saying this. What's this going to look like when I put point 3? Do I put it way down here? Do I put it up here? Is it going faster or is it going slower? What's happening here? The velocity is going in this direction and my acceleration is going in this direction. And acceleration, you want to think about it like this. Acceleration tells me how do I change my velocity over a change in time. And the thing that we really care about is how's the velocity vector changing? Well, in this case, it's changing in this direction. It's going in the opposite direction as the velocity. So this would be decelerating. The object is going this way with the velocity, and we're decelerating. It's like putting on the brakes, and it's getting slower. How do I do this? Well, I just take my acceleration vector and I draw it next to my velocity vector like this. Because this is equal to my change in velocity, that means this right here, the thing that's left over, this is my next velocity. This would be v2. And that next velocity would be this guy right here. Now, it's a little bit smaller than I think I would draw it with our small acceleration. But if you want to take an acceleration to predict your next velocity, all you do is add these two up, tip to tail, and whatever's left over is your new velocity. Okay? And B is our correct answer there. So you have a good, well, your textbook has a handful of these, but this is a good box to look at for motion diagrams. In your packet, it's going to ask you to draw a complete motion diagram for some things, and make sure you have this list on your complete motion diagram. I want to point out some of these things that are highlighted. There's only one velocity vector linking every two position dots, and we've been doing that for all of our diagrams. So for something like this, one velocity vector linking all of those, okay? For each dot that has a velocity vector on both sides, there's only one acceleration vector linking the two velocity vectors. So your dots at the beginning and end will not have a velocity vector. If the acceleration is 0, we're going to write a equals 0. Or you can just use their symbol that the book uses here, 0 with a little symbol above it, or vector symbol, okay? So make sure your complete diagrams have all those things in them. Let's look at a couple more examples. When you have an object moving, we commonly use these terms in just everyday language, speeding up and slowing down. In physics, everything that is an acceleration, both speeding up and slowing down. I'm sorry, let me say it again. In physics, an acceleration includes speeding up and slowing down. There's no distinction. So if we're slowing down, we're going to still say it's an acceleration. Even though in common language we might say it's decelerating, we can still use that term. But when we're writing A, it's still A. The acceleration equals some number or some vector going in the opposite direction as the velocity. So speeding up, if acceleration and velocity vectors point in the same direction, you're speeding up. If acceleration and velocity vectors point in the opposite directions, you're slowing down. And so we go back to this one. We were slowing down because my acceleration is pointing in the opposite direction of my velocity, making my velocity vector get smaller. You can slow down in any direction. Okay? Constant velocity, your acceleration is 0. So this would be speeding up to the right. The velocity vector is going to the right, and the acceleration vector is going to the right. So I would add this vector and this vector to get my next one. It gets larger, and it gets larger, and it gets larger, and it keeps getting larger and larger, and we're speeding up faster and faster and faster. Here, our velocity is going to the left, and our acceleration is still to the right. So look at this. We still have the exact same acceleration, but this one would be slowing down. We would say decelerating it in common terms because these vectors are opposing each other. And so over time, this velocity vector is getting smaller and smaller and smaller. Okay. See if you can answer this question. A cyclist riding at 20 miles per hour sees a stop sign and actually comes to a complete stop in 4 seconds. He then, in 6 seconds, returns to a speed of 15 miles per hour, which is his motion diagram. Take a second, pause the video, see if you can answer that. I want the cyclist going fast at first and slowing down. So let's look at this. This one is going fast at first and slowing down. Look at our velocity vectors getting smaller. Okay, this one's going fast at first and slowing down. This one is going fast and slowing down, and this one's going fast and slowing down. So that doesn't help me very much yet. But let's look at our acceleration vectors. If I'm going to slow down, the acceleration has to be in the opposite direction as the velocity. In this case, if I drew this arrow, I should be speeding up. The next vector would be larger. So it cannot be A. Is there any other one like that? Well, D is also like that. This vector right here for my first velocity would get larger for the second velocity if this arrow is going in that same direction. And so this cannot be the case. That's speeding up. Okay. Let's go to our next little part. He stops at 4 seconds. Let's just do our counts. 1, 2, 3, 4. Here's our stop. 1, 2, 3, 4. This one's a little bit longer. Okay, so we're trying to compare both of these, and let's do this one. In 6 seconds, he returns to a speed of 15 miles per hour. Our velocity or acceleration vector is going in the same direction here. Well, in this case, yep, we're getting a stop here, and we're speeding up. As we add our acceleration vectors, our velocity gets larger and larger and larger, and we have the same thing happening here. So what do we want to do? We just want to figure out our time period. So we have 1, 2, 3, 4, 5 points. 1, 2, 3, 4, 5, 6, 7 points. What is this? This is 1 second, 2, 3, 4 seconds. Those don't line up. B is our correct answer. I'm not sure why our seconds don't line up there. But B is our correct answer. We have too many dots on C between our initial and our final here, and too few dots at the end. We want to have more dots at the end after we stop here than we have at the beginning. Okay. Determine your sign of position, velocity, and acceleration in your packet. You need to decide if things are positive or negative. So we're going to just stay in one dimension, and here's our rules for one dimension. Our positive x-axis is our positive x direction. We define the origin as 0, and anything to the left of the origin is going to be negative in the x direction. So if we have an origin of 0, any point to the right side of it would be a position that's positive. Anything to the left side of it would be a position that's negative, the x position. For velocity, it doesn't matter where we're located on here. Velocity, anything going to the right, even if we're to the left of the origin, if we're headed towards the rightward direction, then we're going to be positive. This would be a velocity equals a positive number. If we're headed to the left, this equals a negative number. Acceleration, if we're headed to the right, it equals a positive number. If we're headed to the left, it equals a negative number. Now, don't confuse these two with accelerating and decelerating. If we want to know if we're speeding up or slowing down, you have to compare these two vectors and see is the velocity and the acceleration going in the same direction or opposite directions. If we had this pair of vectors, we would say we're slowing down. If we had this acceleration paired with this velocity, we'd say we're speeding up. So don't use your sign of acceleration to figure out if you're speeding up or slowing down. You have to compare your velocity and acceleration directions. Okay. How does this work in the vertical direction? Here's how we're going to define our vertical direction. The y-axis, wherever we define 0, and you can define this wherever you want. For any problem, you'll see why we choose certain zeros to make certain problems easier to solve mathematically. But if we choose this as our 0, anything above this would be a positive. This would be a positive y direction. Anything below would be negative. And then we do the same thing for the general definitions for up and down. If you go up, we're going to say it's positive velocities. If we're going down, it's negative velocities. And if we're accelerating, if we're going up, with our acceleration vector is positive. If we're going down, it's negative. Okay, so let's look at this. Determine your sign. You're going to have some of these in your homework problems. Okay, a ball is tossed straight up in there. At its very highest point, the ball's acceleration vector is, where does it point? We did this on our last video. The ball going up, the ball coming down. We want to know what's the acceleration at point 3 here. How do I do that? Well, I want to go back to this. It's a good review again. We want to figure out delta V. That's V final minus V initial. Let's do all the work for this instead of just jumping to an answer. What's V final? That's our V3. So this is going to be V3 minus V2. Okay, that's my change in velocity vector. Let's find that by writing it. So I draw V3. Here's V3. It's going down. And then I take my V2 and I make it negative. So V2 is going up. To make it negative, I just draw it down. And then I'm going to add that to my V3. Remember, this is how we do vector subtraction. We add the negative of our V2 to it. And so if I do that, it's going to be tip to tail. I go to the tip of this one, and I draw my next one. Negative V2 is going to be downward. And they're the same length, V2. So my change in velocity is going to be this guy right here, from the beginning to the end, where I ended. This is my delta V, which means my acceleration is in the same direction, because acceleration equals the change in velocity divided by my time interval, and the acceleration is always in the same direction as that change in velocity. So this would be downward. If I put an acceleration vector on here, it'd be like this. At the top of that path of travel, the ball pauses for 1 second, it stops, and it has to have an acceleration downward to start that downward path. If the acceleration was 0, it would just stop there and stay there forever, because the velocity would be 0 and the acceleration, that change in velocity would also be 0 and it'd stay forever. If it doesn't do that, it comes down, so the acceleration has to be downward. And that's our correct answer. It points down. Okay, that's C. Okay, the motion diagram shows a particle that's slowing down. The sign of position, x, and the sign of velocity, vx, r. Take a second to answer that. Okay, position, I just go to my 0, and I want to know where is my particle. It's to the right of that, so it's a positive position. It's going to be these two. The sign of the velocity, it's headed to the left. If it's headed to the left, that's a negative velocity, so it's got to be B. Okay. The motion diagram shows a particle that is slowing down. The sign of the acceleration is, remember, it doesn't matter. We're not talking about accelerating or decelerating. We're not talking about slowing down or speeding up. We only care about the direction of this. It doesn't matter to us about this part. It just wants a sign. The sign is to the right, and that means it has to be positive. And that's all you need for that. Okay. You have little diagrams like this. Make sure you walk through in your packet showing all the steps, just like I did here. I did it multiple times for you in this video. You're showing all of this when you're showing how you get your acceleration vector. And I want you to practice all that. There's a good reason for that when we start talking more about acceleration and you have to conceptualize it. We're just looking at how acceleration compares to different points in time. Okay, so make sure you draw all of that we did in this video, okay? When you do your complete motion diagram, make sure your diagram includes all your velocity vectors, and every dot that needs an acceleration vector, that'd be every dot except for your top one and bottom one, should have an acceleration vector. You do not, when you do these exercises, have to go through all the steps to show me how you got A, but you should have the correct direction and a relative size of A. Okay. For this guy, you have to assign your positives and negatives. I'll do your first one here for you. We want to know, I want to help you with this notation. This is my initial X position. So for A, I'm going horizontally. So I'm in the X and not the Y. So I'm just thinking about it like this. Okay. This would be my final X position. So this is X0, this is X1. And we want to know, is this positive or negative or 0? For A, we're starting with 0. So this would be 0 for X equals, you can write out like this to keep track of it. My initial X position is 0. My final X position, X1, is positive because it's to the right of the 0. Okay, let's look at our velocity. We're headed to the right, and we're headed to the right the whole time. So my initial V0, that's this guy right here, V0 in the X direction. That's what this means. This guy is positive and it's to the right. So V0x equals a positive number. At the end, this last one right here is V1x. This is also positive. It's a smaller positive, but still positive, and it's to the right. So I'm going to write it like this. Okay. If we keep going, we want to know the acceleration. Now, they didn't draw the acceleration vectors on here, so you have to think about this. My velocity starts out large and it gets smaller and smaller and smaller. That means my acceleration has to be in the opposite direction of the velocity. It's slowing down. Now, this is an acceleration pointing to the left, and that acceleration, AX, is going to be negative. And it's a negative the whole time. Okay, so that's how you fill out those little diagrams there. I think that's it. Yep. I hope that helps for your accelerations. Send me questions if you have any, and I'm excited to get back and help you guys out in person.